Okay, so let's start. Hi, everyone. Thanks for joining us for the session today. Let me introduce Jeff Hammond. Jeff Hammond is a principal programming model architect at NVIDIA. He was involved a long time with the NWChem and is going to give us a short interview to the application. We're going to talk about the tasks and we'll leave some a few minutes for questions if you have anything you want to ask. Jeff, go ahead.
Thanks. So I'm going to go fast through parts that you don't need to know really well. So if you feel like it's overwhelming and I'm going too quick, know that I'm doing that because I want to say the things, but I don't expect it to be hugely impactful, and that'll then allow me to go a little bit slower on the things that I think matter. And of course, this is being transcribed and recorded, so hopefully there's some utility in saying things at all. So I'm going to, this is actually an old outline. I'm going to talk about NWChem, and then I'm going to talk about some of the software variables. And in particular, the reason it says ARM here is just because NWChem is an application that runs on anything, and knowing that it runs on ARM means it's not specific to Intel or AMD or anything like that. But I'll go through all the details, and then I'll show some core scaling numbers with Xeon and an ARM chip, just so you have some intuition about how things are going to work. I very intentionally did not do all the actual assignments for you, even though I could. Because obviously if I gave away all the answers, that would be kind of silly. So NWChem is a very large, very complicated computational chemistry code. If you're not in the chemistry community, you may not have heard of it. I used to describe it sort of as a Microsoft Office of chemistry. So it includes a number of different components. Some people don't touch many parts of NWChem. I only run 3 modules out of the 10 or so that are in there on a regular basis, and then there's some shared capability. The things that matter in NWChem are what's known as density functional theory and coupled cluster theory. Those are the 2 most popular methods in the computational chemistry business of the quantum variety. You may have heard of density functional theory because of codes like VASP and quantum espresso. They use a different formalism than NWChem does. NWChem is more similar to the games code or the Gaussian code. If you've heard of those are very old codes. There's a bunch of other stuff, doesn't matter for the purposes of this activity. NWChem has been around now for over 20 years, and it was designed with process-based parallelism in mind in the form of something called global arrays. I will talk about global arrays. For your purposes today, thanks to 20 years of development and other things, global arrays is a library that sits on top of MPI with a variety of details of how that happens that I will describe, because that is probably the most important thing. For historical purposes, global arrays actually predates MPI, and there's some interesting stuff there that you may care about, but doesn't impact your task. There are reusable components building up the quantum chemical or quantum, basically in the Schrodinger equation, you have matrix elements like the Coulomb operator and the kinetic energy operator. Those things are called atomic integrals in maybe a classical simulation thing. Like if you're doing structural mechanics, you talk about matrix elements formation like the stiffness matrix or the relaxation matrix or those sorts of things. Finite element codes. It's sort of like that, different math. Again, this is all going to be invisible to you for this task. There's an object-oriented design in old school Fortran. We are introducing more new school Fortran of late, but we're not using any modules or stuff like that. So you'll think that's a little bit crazy. It's kind of like saying template metaprogramming in C. Obviously, it's a little bit silly, but know that this is a Fortran code. It is designed around the principle of portability. So we support, to the best of our ability, every single Fortran compiler, no matter how awful or weird. And that limits us to use Fortran features that are very widely available. and work the same everywhere. So we limit ourselves in this respect. If you are not a Fortran person, it's okay. There are very little Fortran specific things that you will actually understand. The code looks a lot like MATLAB or very basic MATLAB. If you understand C or Python or Julia, if you understand anything, you will be able to understand NWChem, because the vast majority of NWChem is written in a dialect that looks a whole lot like something like Algol 66 from a computer science paper. So it's not designed to confuse you. It's pretty easy to understand the math. We have some OpenMP. There's obviously OpenMP in the BLAS and LAPACK libraries that is not visible to NWChem, and then there's explicit NWChem OpenMP and some other things, including CUDA and OpenACC nowadays, which may be relevant to your task or may not. This is obviously part of the challenge, is understanding where the bottlenecks and what are the performance variables that matter. And there are essentially too many variables for any one team to conquer them all in one task. So I would encourage you to think about where your expertise is and what you are interested in studying, so you can look at those in some detail. I just, in part because I'm old, or I feel old, talking about NWChem. For if you're a student and you're in the cluster challenge, most likely you're a few years younger than me, and I think I have to tell you that you may look at NWChem and be like, why did they do that? NWChem was born in 1992, and a lot of things that are absolutely standard normative assumptions in HPC today were not in those days. NWChem is older than MPI. It's older than the practical available implementations of Fortran 90. It's around the same age as POSIX, which is sort of the C standard library, pthreads and the like. It predates Linux. It predates OpenMP. It predates C++ as a standard. I can't see NWChem visibility past 1998. But please know that computers weren't always as beautiful and easy to use as Ubuntu makes it seem. And this is why NWChem does some of the things it does. You won't have to see most of this, but if you start looking through the code, or you look at our build system and are sad, please understand that our build system exists the way it does because we've had to support some very, very strange computers over the years. And the good news about all this is, because we have suffered greatly for many years to make NWChem work everywhere, it should be relatively easy to work on any modern system, although it is maybe not as easy as a AutoTools C++ code. Only to say, on the hardware side, things have changed a lot. The only constant since NWChem was born is basically the Beowulf cluster model. That's basically what everything is nowadays. So, from an NWChem perspective, we have distributed memory parallelism via MPI. We have shared memory parallelism within the node via interprocess communication, which is often taken care of by MPI, but sometimes is taken care of more directly by the POSIX sysv type stuff. And then we also have some heterogeneous parallelism, threads and GPUs, which is not holistic throughout the code, but is in the important parts. And this has been actually a good decision that NWChem has been able to survive through a relatively rocky period in the hardware history by not assuming anything particularly specialized in terms of the platform. I'll skip this, other than to say there's a hierarchy of modules. You won't see this in your task. Global arrays as a programming model is designed to make distributed memory programming easy for a quantum chemistry type person. So when they designed NWChem, they had some computer scientists, but they knew that they would have to hire actual chemists who knew domain science and who knew Fortran, and make it possible for them to program distributed memory systems, which in the 90s was novel and difficult. It's not necessarily easy today, but I think most people nowadays understand MPI or can use it if they're in this business. So global arrays is a higher level model where the central object unlike MPI, it's not communicators and messages. It's you have a distributed array, a dense array, and you put data into it. You accumulate data into it, which is like an update mathematically, and then you get. So you could think of it, a friend of mine once described it as a big parallel RAM disk. If you don't know what a RAM disk is, it doesn't matter. Basically, you could think of it as a file or a database-like abstraction, only it's stored in memory, and it is oriented around double precision multi-dimensional arrays, which is, of course, what the scientific codes need. If you look at NWChem, you will not see a lot of process indexing. You will see global arrays construction, create, and then you will see data parallel operations like zero it out or diagonalize it. And then you will see operations like grabbing a block of data from an array, doing some work on it, and then putting it back. And that's the central model for NWChem's distributed memory parallelism. It works remarkably well until it doesn't. Usually you can strong scale only a limited degree, but you can weak scale pretty effectively. Nowadays, this sits on top of MPI. It sits on top of MPI send receive or MPI one-sided communication. Historically, send receive have been much more tuned and more reliable in MPI libraries. I think everybody understands that that's the common use case. So NWChem will use send receive in the sort of standard backend, and that's good. It means you don't have to think too hard about this. There's also a module or an implementation using one-sided, which I am responsible for in part. And you can view this as one of the key performance variables. It will depend greatly on what your network is and what your MPI library is. This is probably the biggest performance variable, and Gerardo knows because he has been running an enormous number of these experiments lately so that you hopefully will suffer less. There can be some pretty significant negative performance issues if you use the wrong configuration. Hopefully you'll be able to pick a configuration that's relatively straightforward, and I'll certainly tell you what the easy buttons are. But we do have a lot of data, so we can hopefully prevent you from wasting time on this. The global arrays model, it doesn't matter too much detail, but under the hood, one of these matrix-oriented operations is translated to one or more operations that go across the network. If you profile, which is one of your tasks, you will see that, what you'll see in an MPI trace is send and receive, and if you do it to try to understand where the traffic goes, it won't actually make sense. And I'll just tell you right now, it's not supposed to, because you write data-centric parallelism. So when you do an operation, it goes and scatters it across the network. And so there isn't this beautiful structure like you'll see in a heat equation solver where you see nice banded communication patterns. You shouldn't really try to understand this. The good news is with today's networks, fat tree networks and shared memory, you won't really notice the difference. But this is just something to think about what's happening under the hood with the communication. And depending on which MPI conduit you use, how these things show up in your profiles will depend. So if you use the send receive based protocol, you'll see one trace pattern, and if you use the one-sided communication MPI stuff, you'll see a different trace pattern. They're ultimately doing the same thing, but they're doing it in different ways, and that'll impact what your trace looks like. We've moved to MPI-based ARMC just because MPI is everywhere. Some of you may discover that there's InfiniBand verbs explicit implementations. Those are unsupported. They do sometimes work, and they do sometimes work well. They also sometimes don't work, and that's the reason why we don't assume them, and I'm not recommending them to you. If you have an InfiniBand network and you use verbs, you might have some luck. But if you have problems, know that there's not a lot we can do to help you. It's either going to work or it's not. This is documented in more detail on the wiki page that I wrote, so I'm not going to go into it in detail. This is just to say there are many ways to map global arrays in NWChem to MPI. there are two paths that you should attempt, and only two. One is called MPI-PR. The exact details are documented on the website. The other is RMC-MPI. Both of those are used regularly. Those are the ones that I've run extensively. If you use RMC-MPI, you need an MPI library that does one-sided communication correctly. I have found that Intel MPI is quite good at that, as is MPitch and NVIPitch. OpenMPI, it depends greatly on the details. In some cases, depending on the network, it can behave very badly. In other cases, it's fine. As a cautionary statement, to be conservative, if you're going to use RMC-MPI, I would not use OpenMPI unless you're willing to go through a great deal of work if you get bad luck. Okay, so if you try it and it doesn't work, you may be in for a long haul. If you use MPI-PR, as far as I know, there should not be any issues. It should just work. There are scenarios where it will work better or worse. It depends on the details. But I want to throw that out there. I do intend to support all these issues, in real time to the greatest extent possible. So if you start on this path and you want to try lots of things, I applaud you. But start early, as you will not find that this is pleasant to do on, say, 24 hours notice. I'm going to show you as a simple example with the density functional code. This is a very standard benchmark problem that's been used in other scenarios. Just to show you that if you use RMC-MPI with Casper, I believe it's described on the website, you can get the same results as MPI-PR. This is good. What it says is if you do it correctly, you get the same results, so it shouldn't matter. Problem is, if something goes wrong on either side, it can go worse. But I wanted to throw this out there that, there's a small difference in some cases. RMC-MPI is a little bit better. In some cases, MPI-PR is a little bit better. It will depend on your network. This is a key performance variable, and I will say the reason it's an interesting challenge for you all is it's a huge part of my day job, and one of the things that I have to do on a regular basis is study this. So it is real-world education, not just some academic problem to go study this. Just to show you that how far you can take this, if you push it in every possible direction with tune all of the communication, tune all of the MPI plus OpenMP within the node, use the best possible OpenMP configuration, you can run NWChem on 500,000 cores and hit 9 petaflops, which in this case is right around 50% of peak. I can't remember I did the math at one point when I worked at Intel on exactly how much percentage peak is. But you can make NWChem do this. It does take some work. You have to tune all the parameters. The good news for you all, or the bad news if you like hardware, is that you won't have 500,000 cores at your disposal for the cluster challenge, and therefore you won't have to worry about all of the things that go wrong at this scale. Obviously, knowing that you have to pick 57 out of 68 cores and tune all the stuff in the right direction, that can be tricky. You won't have to do that. You should not have anywhere near that level of sensitivity on the AMD and Intel Xeon nodes that you'll be using. So, software requirements. Basically, in a CPU sense, everything works. So, every CPU that we know of, we haven't run on like MIPS or Itanium in a while, but PowerPC, ARM, and Intel, AMD all work fine all the time. We test this stuff on all the DOE supercomputers on a regular basis. There is GPU support. I work on that because I work for NVIDIA. I've done stuff with OpenACC and some CUDA Fortran stuff. There's also OpenMP. I don't have as much experience with that now. I've worked on that in the past when it was relevant to Knight's Corner. My friend Michael Clem at AMD works on that now. So if you come to the cluster challenge and you happen to have an AMD GPU, you may find that to be relevant, but you will want to start early and work in contact with the people who've written this stuff, because the GPU stuff, the building that can be a little bit challenging. All the operating systems are supported. I'm sure you're using Linux, so it won't matter. Linux is fine. All the major compilers, meaning GCC, Intel, and NVIDIA, or aka PGI, work just fine. There are some challenges with the Fujitsu compiler. I think the Cray compiler is working now. I assume these are not relevant to you in the cluster challenge, but if they happen to be relevant to you for any reason, know that we do try to support every single reasonable compiler out there. I believe that AMD Flang and ARM Flang both work, although I don't actually test those on a regular basis. I assume some of my friends at the other companies do. So, you should be fine. All the math libraries work. So, if you use a math library that we haven't heard about, you may have to add a preprocessor macro to do one thing. Don't worry about that. If you hit it, it's a 30-second fix I can tell you about. But things like netlib, MKL, OpenBLAS are all fine. You can ask NWChem to build OpenBLAS for you. That's probably the easier button. I'm kind of a Luddite, so I always build BLAS myself, or at least install it separately. You shouldn't have to do that. MPI is always assumed, but the way we configure with MPI, we don't use the wrapper scripts. Please don't use the wrapper scripts. They do cause problems. You need to just unroll the wrapper and say, here's where the MPI headers are, here's where the MPI library is, and use that. Those examples should be documented. MPI PR, like I said, works with everything. ARMC MPI sometimes works with OpenMPI, but I've had problems lately that make me sad. So just be careful. In my experience, in part because I worked with them for a number of years, Intel MPI works really fantastic with ARMC MPI. MVPitch should also work just fine. If you're using any MPI with the open source, if you're on InfiniBand, please use UCX. That's written by Mellanox folks. I know that UCX is better than anything else that's in there for Mellanox networks. If you're on another network, libfabric may be better, and OpenMPI and MPitch both support these. Don't use any of the older stuff. There's like OpenIB and PSM2 and some of those things, and I would caution you that they may work, they may not, but if they don't work, those are slightly older protocols, and may just be a dead end. Performance variables, you'll see on the figure in just a second. What I'm going to show you on the next slide is that there's actually a pretty low sensitivity to the software config, and that's at least in shared memory. If you go across the network, MPI starts to matter more. But this is just to say, on an Ampere system where I compared the NVIDIA compiler to GCC, it doesn't really matter. I would say it is known in some cases that the NVIDIA compiler or the Intel compiler or the Cray compiler can give you better results. There's a whole bunch of cases where it doesn't matter at all. So please, to save yourself the trouble, get everything working with GCC the first time through. You will be happier. If it doesn't work with GCC, it's not going to work with anything else. So please get all your problems out of the way with GCC. You will find that OpenMPI and MPitch, at least in shared memory, make almost no difference, and that ARMC MPI and MPI PR make almost no difference. There's up to a 10% effect that comes in at smaller process count. MPI PR takes one of your processes and turns it into a network engine, so you don't actually use it for compute. If you have 4 cores and you take one of them away, obviously you notice 3 out of 4 is a noticeable fraction. 63 out of 64 is not a noticeable fraction. So if you are running on a big server, this effect basically goes away. And so you want to dedicate a process to communication. It's going to improve your performance. You can do this with ARMC MPI. You can do more than one with both. If you really want to go down that path, please start asking questions in the forum for that as soon as possible, because it may require a little bit of work. Skip that. You can read it if you need to know it. This is scaling. This is strong scaling within the node. What you see here is pretty good scaling out to 32 cores. After about 40, it doesn't scale perfectly. So if you bring a really, really big node, you may not get perfect scaling. If you're using the nodes that I believe we're providing, which may in fact be necessary because that's what the virtual hackathon will be, then this shouldn't be an issue because we don't have more than 64 cores. But just know that NWChem runs out of scaling at some point within a big server node. The same thing is true is in multi-node scaling. If you scale from 1 to 4 nodes, the scaling is usually go from the 1 to 2 node scaling can be rough because you go from shared memory, which is super nice, to distributed. Sometimes it's actually not a very good scaling curve, but then it starts to go down after that. If you run a really big problem and you start with 4 nodes, you can usually scale out 10, 12 nodes. But most of the uses of NWChem are to run bigger problems on bigger systems. So we don't care as much about strong scaling the way some of the other application domains do. I'm almost done. Yeah, I wrote the page, and Rado has gone through and debugged it and found things that I didn't do perfectly. You're welcome to ask me questions about all this stuff at any point. Supporting NWChem and ARM CMPI is part of what I do. But I tried to the best of my ability to write as much as I could on the wiki without being overwhelming. That's a fine line, and I'm sure that I overwhelmed some, and for other people didn't provide enough details. But I'm done with the presentation, and please take as much time as you want for questions.
So anyone has any questions? Parallel.
Don't all start asking questions at the same time.
Yeah.
Preguntas, Frage.
Excuse me, can I ask a question?
Sure.
Yeah, I'm a student from Georgia University, and I have some problems in building GPU tasks for running NWChem. So I wonder whether I can find some specific instructions in the documentations of NWChem.
That's a good question. So please email me or NWChem user list. You can email me especially if it's my code, so I'm not publicly embarrassed by my mistakes. The CUDA version was written CUDA C version of TC was written 7 years ago or so, and is not actively maintained. However, it should work. But the recipe to make it work may not be properly documented in a nice way. But I can figure it out and I'll work with you. If you are trying to build the OpenMP stuff, that is an interesting question. I haven't done that. If you're trying to build the OpenACC Kublas version that I wrote earlier or last year, that's definitely, I can give you a recipe for that I use every day or close to every day. But sadly may not be in a great place online. I confess, in some cases, some of the NWChem developers are either not paid or they're paid to write chemistry papers, not documentation. This is one of the sad realities of being a grown-up and not getting paid to do things that probably should be done. So I apologize for the documentation.
Thank you very much. I'm sending your email.
Okay.
Let me add another thing. So we have 2 clusters that we are going to use for this application. One is the Niagara cluster. We used it last year. It's Intel cluster with the Skylake CPUs and 40 cores per node. And we have the Bridges 2 cluster PSC. And over there we have AMD nodes with 128 cores per node. And we have also few GPU nodes over there. So I will later on in this upcoming 2 weeks, I will send you details about those clusters. You already used for the bridges too, you already created your account and you're supposed to have access there. So I will announce it later. Check that you can access and use the cluster. And I will check the status with the Niagara cluster. But it's supposed to be given to you in the next 2 weeks. About the input files, you're supposed to generate them as stated in the wiki. And then Jeff commented on the NVIDIA on the procedure for the V100 over there. So there are V100 GPUs on the Bridges 2 cluster. Okay. Gerardo, do you have any additional comments? Anyone feel free to ask.
Yeah. So for context, the input generator exists. I made it because I'm lazy, which is to say, it's there as a convenience so that you don't have to ever understand chemistry to run NWChem benchmarks, which has been something that's been important to a lot of people over the years. You can use the benchmark generator to generate a file and then hack on it all you want, if for whatever reason that's your thing. You're not required to use the generator like any more than it will at least save you the trouble of getting to the thing. It can be really nice if you're for automating things. As far as I've used it almost every time I've run NWChem for the past decade. So I hope it works. If it doesn't, feel free. It's fully my fault, and you can go to the GitHub repo and complain if you have any issues with it. The only requirement last time I checked was I did update to Python 3. You shouldn't use Python 2 anymore.
Okay, let me add another thing. Is most clusters, you may have older MPI libraries, modules installed. You can just compile and use your own version of compiler or your own MPI, and you don't have to use the modules that are installed on the cluster. I mean, you can, but sometimes it's not always updated in the last ones. Okay. So last thing, in addition, we have, of course, the Slack channel. You are welcome to use it, ask questions, contact us for anything, any concerns, any problems you have. I would say we'll try to help you as much as we can. Okay, any additional comments, questions? Anyone wants to ask anything? Okay, so thanks everyone. Thank you, Jeff. And we'll continue with the Slack and ping us for any question you have. I will update in the next 2 weeks about the cluster access, so you can start testing. Okay. Okay. Thank you, everyone.
Thanks, everyone.